Hello guys, let's prove the binomial theorem. So, the binomial theorem states that or gives the expansion for a plus b to the power n, or simply the expansion for any two terms raised to the power, well, any power. So this is equals to c n comma 0, where c is stands for combination. So if you have c n comma r, this will be n factorial by n minus r factorial into r factorial. This will be a to the power n b to the power 0 plus c n comma 1 a to the power n minus 1 b to the power 1 plus c n comma 2 a to the power n minus 2 b square plus dot 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 plus c, let's say n comma r, e to the power n minus r b to the power r plus all the way to the last term c n comma n a to the power n minus n b to the power n. So obviously a to the power n minus n is 0, a to the power 0 is 1, and here also b to the power 0 is 1. So in the first term we'll always have a to the power of the, well, the binomial a to the power n b to the power n. So basically the first term will be to the power of its, well, of the original power, and the last term will have the second term to the original power, which is n. If you put r as 0 over here, you'll see we'll have n factorial by n factorial into r factorial, which is just 1. So we'll just in fact have a to the power n and b to the power n. That is just a fact over there, and we're actually going to have to prove this combination over here. And to prove this, we need to use one combination fact or property: c n comma r plus c n comma r minus 1 is equals to c n plus 1 comma r. Now if you want to prove this, you can just put this over there and this similarly like this, add them up, do some algebra, and hopefully you'll get this. So that's another thing you can do. Maybe you can pause the video and try this out. We'll do the proof by just simply adding, but in the end you'll just get this. And yeah, let's just start. So I've given you guys the hint to use induction, namely proof by mathematical induction, to prove, well, this binomial theorem is legit. So there are 4 steps in the mathematical induction proof. First is you have to let Pn be, well, the equation, right? Well, what we're trying to prove, which is C. And right here another interesting fact is this combination are called binomial coefficients, and this combination we can just write it as C0, because here you can see we have c n comma 0, n comma 1, n comma 2, blah blah blah. Well, instead of that we can just have c naught a to the power n plus c1 a to the power n minus 1 b to the power 1 plus dot dot dot. However, for this proof it's in fact better if we not write that, but I just wanted to give you guys the quick fact. So let's just write it as how it is. So it's this: b to the power 0 plus c n comma 1 a to the power n minus 1 b to the power 1. Let's not write the two part, plus c n comma r a to the power n minus r b to the power r plus dot 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 c n comma n a to the power n minus n b to the power n. Now this is the first part for the mathematical induction. Now for the second part, we just simply have to prove p of 1, namely just put n equals to 1, n equals to 2, n equals to, well, I don't think 0, but n equals to 3, whatever, and this should be true. So if we let p of 1, then on the left hand side we'll get a plus b to the power 1. So we'll just have a plus b on the left hand side, and for the right hand side we'll have first c n comma 0 a to the power 1 plus c n comma 1, or let's just write b to the power 0 a to the power 1 minus 1 b to the power 0, and well, not n 1, because here n is 1, so that minor mistake. And this will just be equals to a plus b, because 1 comma 0 1, this is just 1, we have a plus b. So this proves that p of 1 is true. Now for the third part, this is the part where it gets interesting and the induction starts to take place. So we'll have to suppose here, we have to consider that, let's say for p of k, or for p of k it is true. So simply let's let pk be true. That is, well, a plus b to the power k is equals to c n comma 0 a to the power k b to the power 0 plus c n, oh not n, k comma 0 k comma 1 a to the power k minus 1 b to the power 1 plus dot 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 c n not n, k comma r. It gets a bit confusing, don't worry. K minus r b to the power r plus dot 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 c k comma k a to the power k minus k b to the power k. Now for the fourth part is where, well, we prove it. We need to prove whenever pk is true, then pk plus 1 should also be true. The induction works like this, because here k plus 1 just refers to the next number. So if it is true for the next number when the previous number is true, that means that p of n will be true for whatever integer, right? So because here, if the previous number is true, then the next number is also true. That means that the next number from the next number will also be true, and the numbers after that all will be true, because, well, the previous number will be true. Thus induction works. And we need to prove, so we need to prove this part, pk plus 1. So a plus b to the power k plus 1 is equals to c k plus 1 comma 0 a to the power k plus 1 b to the power 0 plus c k plus 1 to the comma 1 a to the power k plus 1 minus 1 b to the power 1 plus dot 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 plus c k plus 1 r a k plus 1 minus r b to the power r plus dot 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 c k plus 1 comma k plus 1 e to the power k plus 1, I'll just write 0 b to the power k plus 1. Now we have to prove this, but how? Well, generally if we want to prove p of k plus 1, we have to use what we're given. So think what we're given. Well, this is not actually given. We're just establishing this is what we want to prove, and we're proving one of the condition, the specific condition, and we're given that pk be true, right? Or be true, that sounds a bit piratish. pk is true, so we have considered this, and this is given. So we somehow have to use p of k to get pk plus 1 to be true. Well, we have p of k, and in p of k plus 1, we simply have a plus b to the power k plus 1. So if we have let this be true, then let's just multiply the left hand side and right hand side by a plus b. Because here in the left hand side we'll get a plus b to the power k plus 1. Indices law, of course, the power add up, and we will just have to multiply all of these terms by a plus b. So, and I've written many of these terms because it will be necessary to understand the pattern for how we can prove this using induction. So we will have on the left hand side a plus b to the power k plus 1. This will be equals to, now this will get a lot crazy and very lengthy, so bear with me. And I'll just multiply these terms out and I'll be right back. So I have multiplied a plus b to the terms you can see here. So we have all of these terms, which seems a bit crazy, but all you need to find is a way to somehow get this. You somehow need c of n comma r, or in this case k comma r plus c k comma r minus 1 equals to c k plus 1 comma r, or well, that will be equals to this. Now you have to find such two terms. That means we have to somehow take these common, right, these a and b terms, so that we can use this combination property. So let's just directly move on to the general term. So this is it. So we have this right here, but as you can see the power is different. But what about this? A to the power k minus r plus 1 b to the power r, and here also a k minus r plus 1 b to the power r. They are the same. That means we can take that common. And inside the bracket we'll have c k comma r plus c k comma r minus 1. Exactly what we needed to have this. And well, this will be k minus r plus 1 b to the power r. This will be c k plus 1 comma r. Now you can rearrange a term like this. So this will be c k plus 1 comma r, a to the power, instead of k minus r plus 1, what I can do is k plus 1 minus r, and in fact to make it clearer I'll write it in a bracket, b to the power r. Now this is the general term for any binomial expansion. Here k plus 1 is the power, and because here we have a plus b to the power k plus 1. So we have c whatever power comma r, just the general term, a to the power that power minus r b to the power r. So this is one of the case, and as you can see we have many of these, like here e to the power k b to the power 1, e to the power k b to the power 1, and when you add these up they will of course take common. You'll have c k comma 1, c k comma 0, which is just 1 minus 1. So these two will make up as c k plus 1 comma 1. And similarly these two over here and these two will inside those terms, and so on and so forth, right? These two terms will have the same power of a and b. They will combine up, and you can use this combination property to get in terms of c k plus 1, which is exactly what we need. As you can see here from the second term, all of the two terms can add up, and up to the second last term. As you can see right here, these and these are same, but one thing still remains, or two things. What about the first and the last term? Because here a plus b to the power k plus 1, when we expand this, the first term will be c k plus 1 comma 0, a to the power k plus 1 b to the power 0, and the last term will be c k plus 1 comma k plus 1 a to the power 0 b to the power k plus 1. And well, thankfully we already have the power of a and b as we need, but we do not have the combination for this. Wait, I wrote it wrong. This is still c k comma k. Sorry for that misinformation, but you can see we do not have the same combination, and over here also we need k plus 1 comma 0. But it's very simple, because here c k comma 0 or c any number m comma 0, they're all equal to each other, because here c k comma 0, if you just expand this, this is just k factorial by k minus 0 factorial 0 factorial. What you'll have is k factorial by k factorial into 1. So in the end you'll just end up with 1. So that means even if we have c k plus 1 comma 0, this will just be k plus 1 factorial by k plus 1 factorial, which will also give 1. And since 1 is equals to 1, you can just replace k with k plus 1. You can just replace k with anything as you wish, but we need the binomial expansion, the right form, so we have to write it like this. And we're now allowed to do this, and also for the last term, because k comma k is, well, this is just this, and this is the same thing. You'll have k factorial by k minus k 0, 0 factorial, which is 1, 1 into k factorial. So you'll also get 1. And that means we can also replace this k plus 1 and k plus 1. And like that, we have our a plus b to the power k plus 1 expansion. Now, I'm not going to write out the next step, which is, or I guess I have to because it's in the proof. So I'll again be right back. So this is a plus b to the power k plus 1 equals to all of this. And I've written fewer terms because you can just understand. And yep, as you can see, this follows the binomial expansion. This follows the binomial theorem correctly, and hence, since p of k plus 1 is true, that, or pk plus 1 is true when or whenever pk is true, therefore p of n is true. That is the proof by induction, and there we go, we have proved this lengthy part of the binomial theorem. And if you learned something new, please like and subscribe. Thank you.